Okay, cool. So this is the second session of our program 1 for MINDNZ. And today we are doing number theory once again. So just a bit of a heads up for everyone. We will recap on the content that we did last session on Tuesday. We'll do a bit of recap and then finish up with what we were doing with the modular arithmetic, like the addition, subtraction, all of that stuff. But then we're going to move on and hopefully try to get through some really cool theorems that are going to be really helpful for Maths Olympiad. So those things, to be honest, I find them like a fair step up because you kind of have to make sure you understand all the foundations, then you put that all together to start understanding the theorem. So feel free to let me know when you want me to slow down, but if you feel like it's looking a bit hard, like don't be deterred. It's probably going to look that way for everyone. Okay, let's get started. Okay, basic rules. I think we probably know them all. Yeah. Just a reminder for you can find course content after class on our website, and also it's good to join our Discord. Okay, so today we'll start with a recap. We'll talk about the addition, subtraction stuff, more of that. Then we'll move on to, oh, I forgot to change the contents page. Please don't look at that. Okay, but we're going to do a few theorems as well. I don't know how I did that. But okay, first, for a recap, what did we do? So on Tuesday, we talked about remainders in division, prime factorization, GCD and LCM, and introduction to modular arithmetic. Does anyone have any questions about that? Anything you're not sure? You want some quick tips, a little bit of, advice on? Feel free to unmute yourselves or, tell me in chat. Okay, that seems to be like everyone's good with it. Awesome. Okay, so then we can move on from that. Now, onto the last section of what we did. So, addition is all we really managed to get through last time. Does anyone have any questions on that? Okay, awesome again. So then we can go through the next few things. So subtraction is basically the same thing. I don't think we have to explain it too much. So let's just do the latter three. So we can do multiplication then. And I'll share my screen on. Okay, hopefully we can all see this. Oh. Hello. Sorry, I clicked the off button on my iPad. Yeah, sorry. Okay, back to it then. So for multiplication, there are a couple of things we want to remember. So the first thing would be the initial conditions, right? So we want if A is congruent to B mod M and C is congruent to D mod M, we get this following result. AC is congruent to BD mod M. Okay, so this thing, I just want to make sure we understand the notation. I'll probably show you guys why it works at the end, but I don't think that's as important as just understanding how we can use it at the moment. So let's just suppose we have A and B, which are congruent to each other, and mod M. So let's just suppose we have like, which will we choose? 11 is congruent to 6 mod m, not mod m, sorry, mod 5. And then we have, how about 10 is congruent to 5 mod m, mod 5, that is. Then how do we apply this multiplication principle to get what AC is congruent to? Does anyone have any ideas? So it's like the same as the addition one, we just plug it in. Okay, yeah, so I can just do a white example first. That's a good idea, actually, because it's a bit hard to jump into. Sorry, I'm sick. Okay, so let's just say we have 11 as A, B equals 6, C equals 10, and D equals 5. Then we just plug it in to get A times C, which would be 11 times 10, is congruent to, on the other hand, we have B and D, so 6 times 5 mod 5. And then let's just match it up so we can all easily see what happens here. 6, 10, and 5. Right, so can we kind of see how we set things to like A and B and C and D so that we can plug it into the equation and get what we want? How do we get the answer for the first bit, the original part? Oh yeah, good question again. So let's just do a quick recap on the fundamentals then. So how do we determine if two things are going to be congruent given a certain modulus m? They're congruent when you have the same remainder. So for example, if we have mod 5, 11 is congruent to 6 because 11 equals to 6 plus 5. Sorry, equals to 10 plus 1, which equals to 2 times 5 plus 1. So the remainder is 1. And then 6 equals to 5 plus 1, which equals to 1 times 5 plus 1. So then the remainder is 1. Does that kind of make sense? So you just want to break it down, and then if they have the same remainder or residue, in other words, then they will be congruent. Does that kind of make sense? We can do another example if you need. Okay, then I hope it's okay, but let me know if you need any more help as well. Okay, so back to this. So this is just the worked example that I've given. So I want you guys to give last time we were working out the mod. We did division or something. Oh yeah, the modulus, right? M is what we're dividing by. And then what we were finding is like B, right? So if we have A is congruent to B mod M, we were trying to find B given a certain A. So we're finding the residue. Yeah, so it was like division. So you found the remainder. For example, like if you want to find like 7 is congruent to what, like in mod 2, then you would find the remainder when 7 is divided by 2, and then that would be 1. Okay. So, of course, oh, good job. That's really good. So let's just do another example because I do want to get through these slightly quicker if possible. So I want to make sure you guys tell me what you think about the pace. If you want to ask questions, please do ask them. Okay, so let's do another one. So let's say, what should we do? (11) is congruent to 4 mod 7, and 9 is congruent to 2 mod 7. Following the example that we did above, can anyone try to figure out what 11 times 9 is congruent to? Can someone try to plug the numbers in and then see how it goes? So it's like the same thing, you let 11 equal to A, perhaps, then 4 would be B, 9 would be C, and then 2 would be D. Yeah, good job, guys. Wow, really good. So it would just be, I'm not sure about that notation, but I get what you're going at with the, with the like exponent thing. But yeah, 4 times 2 would be the right answer. So you would get 11 times 9 is congruent to 4 times 2. And really, really great job to people who have tried in the chat. It really helps me to gauge your progress, and it's good that you're all doing good. Yeah, doing good. So one way to think about it is the same as doing multiplication, like in, I guess, normal arithmetic, right? It's like, because in modular arithmetic, one thing we get is like, if in normal arithmetic, one thing we get is if A equals to B and C equals to D, then A plus C is going to equal to B plus D. It's kind of similar here with congruency, right? And then it would also give the result that then A times C equals to B times D. So it's like kind of the same logic. Does that make sense? And does anyone want to turn their cameras on so I can see their beautiful faces? No, okay. Also, for those of you who don't have your real name as your username, could you please change it so that I can take the role? Because that would just be, helpful for checking up on the attendance and the admin stuff. Okay, so hopefully everyone understands this. No one has really given me a clear indication that they don't. So I think we can move on from this. The next thing would be division, which I think is a little bit more confusing. Okay, I don't think I'll give the proof for the multiplication one now, but I might in like the next tutorial if people want to come and ask about it. And then I won't give the proof for the division one either, because the division one is a bit more complex. I'm not sure if you guys are looking at the handout or not. I think I did send that out. It would be good to look at it, but it doesn't look exactly the same as the other ones, because here we have A divided by E is congruent to B divided by E, mod M divided by the greatest common divisor of M and E, where E is a positive integer that divides A and B. Like that's a lot to process, right? But let's just like, try to break it down a bit. So we want to remember the same conditions as before, which is the only one that applies to this is A is congruent to B mod M. Okay, so it's like, we would think that it's pretty intuitive, right? Because when you're multiplying, like, oh, it's not that weird. Like, suppose we have this part, which is true. Then we multiply both sides by E. Then we're like, AE is congruent to BE mod M. Simple, right? But then that's going to change in division, which is a bit hard to wrap your head around, but it's because we need to consider the greatest common divisor. So when we want to divide, we can't necessarily maintain the same modulus M. So we have to divide that modulus by the greatest common divisor of M and E. And I think we all remember how to find the greatest common divisor, right? Yeah, hopefully. So let's just go through an example of this, then I'll do a worked example, and hopefully that will be good. So let's say, what should we do? 6 is congruent to 2 mod 4. So now suppose we want to find what 3 is congruent to. That would, to find 3, to get the number 3, we would want to divide 6 by 2, right? So then we do that. We go 3, since that's 6 divided by 2, is congruent to 2 divided by 2, which would be 1 mod 4. Is that wrong or right? Someone tell me. Guys, hello. Just guess if you don't know. Like, remember what I was saying before, everything changes? Like, this is the part that yeah, it's wrong. Good job, guys. Good job. Whoa. We're doing it so well. Very good, very good. Okay, so it all changes because we need to divide the modulus, like, by the modulus as well. Divide the modulus by something as well. So then the answer instead would be 6 divided by 2 is congruent to 2 divided by 1 in mod 4 divided by the greatest common divisor of M, which is 4, and E, which we're dividing by, which is 2. And can anyone tell me what this is?
2.
Yeah, 2. Good job. So then what we get is 3 is congruent to, oh, sorry guys, that's supposed to be 1 mod 4 over 2. So then 3 is congruent to 1 in mod 2. There we go. And then if we break it down, that does make a lot of sense because 3 is equal to 2 plus 1, which equals to 1 times 2 plus 1. So we have a remainder of 1 when divided by 2. And 1 is equal to 1, which equals to 0 times 2 plus 1. And we have a remainder of 1. There we go. So it turns out the rule does work in this case. So let's try another example. I'll just probably make this a bit smaller so we can see. You can hold on to it. And then I'll give you guys an example, and then it would be really good if we could try to work through it. So let's do 12 is congruent to 8 mod 4. So let's suppose we want to find why is it 6 divided by 2 and 2 divided by 2? Okay, really good question. So my question for you guys before was we wanted to find what 3 is congruent to. So that's why we divided by 6. That's why we divided 6 by 2 so that we could get 3. And then the reason why we divide 2 by 2 is because if we divide it by 2, then E would be 2. Then E also becomes 2 on the other side of the equation. Cool. Awesome. Okay. Now let's find how about we find what 6 is congruent to? I'll give you guys maybe a minute to think about that. Feel free to type in chat if you need any tips to go ahead if you're feeling stuck. Yeah, it's a bit of a hub because you do need to figure out how exactly it works. I got something to do with 2. Yeah, really good job. Because we want to find 6, right? So then what do we divide 12 by? 2. So that means that we want to do 12 divided by 2, which equals 6, right? Which is going to be congruent because of our rule. It's going to be congruent to, 8 divided by 2. And then can someone help me figure out the modulus part? Sorry.
Mod 4, mod 2.
Oh, mod 2. Is that what you said?
Yes.
That's right, mod 2. Good try to the person who said 1.5 though, because it's a good try, yeah. Because I think, well, not I think, modulus m m cannot be a number that isn't a positive integer. So we just want to be careful about those numbers. What's the GCD? The GCD is the greatest common divisor. So remember when we were what's the greatest common divisor of 24 and 12? And then we would list all the factors, would be 1, 2, 3, 4, 6, 12, 24, 4, 24. Then for 12, we would be 1, 2, 3, 4, 6, 12. And then we would choose the greatest common one, so 12 on both sides. So is it of 6 and 4? Not quite. It's close actually, but it's just about using the right number. So what we want is using the original modulus 4 and the number that we're dividing by 2. So then you get mod 4, which is the original one, m, divided by the greatest common divisor of 4 and 2. And then it looks like someone had already gotten it before, but can someone tell me what the GCD of 4 and 2 is?
2.
Yeah, really good job, Jackie. Yeah, good job, Tara. Awesome. Really awesome. So that means that we get 6 is going to be congruent to 4 mod 4 divided by 2, which is 2. Oh, and good job, Jenny, as well. Okay. Okay, so I'll do another example now. And then, do you think it would help if I color coded it? Or like, no? Like, let me know what you guys think. Like, should I color code? Okay, no opinions. Then I'll just do another example. Oh, yes? Okay, awesome. Okay, so I'll just do another example. Then we'll walk through it and see how everyone goes. And then I think after that, maybe we can do one more example depending on how you're feeling and then move on. So another one that we have would be, okay, let me think of an example. Let's do 18. 12. Should I do? Okay, let's just do it's congruent to 16. No, 15 mod 3. Okay, that looks fine. Then, can someone help me find what 6 is congruent to? If anyone is kind of speeding ahead, feel free to, tell me how you did it already. Otherwise, I guess I would just go ahead. So we want to find 6 on the left-hand side, which means we want to get from 18 to 6. How do we do that? What would we choose as our choice of E? Three. Awesome. Yeah, great job, guys. So then we would go 18 divided by 3. We know that's 6. So let me just highlight E, all the E's, and 3, so you guys know. And then what does that mean for 15? We also have to divide it by E, right? So then we get 3 again. And then that's going to be congruent to mod M. So M would be 3 in this case, divided by the greatest common divisor of M and E. And in this case, M is 3. And then E is also 3. Whoa, okay. So then let's just highlight these. Okay, and then let's just, can I get an answer as to what the GCD of 3 and 3 are? Oh my gosh, good job. That's so good. Really good job. So do you want to tell your answer to the group chat actually? Yeah, good job, Jenny. That's good as well. And also, how do I pronounce your name? Is it Artica or like yeah, can you let me know? Because I don't want to get it wrong. But if you can't like unmute right now, it's fine as well. Up to you. Artica, is that right? Okay, awesome. Really good job, Artica. Really good job, Jenny. Anyone else? Okay, maybe not at the moment. How about you guys share your answer with the group chat? Are you all right to do that? Close, Jackie. Oh wait, for the GCD? Yeah, that's good. Good job. Okay, good job. We can, yeah, okay, we can leave it there. Yeah, really good job, guys. So what I got was that the GCD equals to 3 because you have 3 and 3, right? So then we get on the left-hand side, 6 is going to be congruent to 5 mod 3 divided by 3, which is going to be 1. So good job, everyone. I feel like everyone's made a lot of progress. They're all getting it right. That's awesome. If anyone needs some extra help, yeah, Alicia, let's go. If anyone needs some extra help, feel free to private message me. It's, all good. It's like a pretty hard concept to pick up, Do we need one more example or can we move on? What are your thoughts, everyone? Oh, awesome. Okay. Some pretty big move-ons. Good job. Okay, but if anyone needs any help at all, feel free to message me. We can, schedule another session sometime soon and talk through it for you. Okay, but for now, we will move on. Really good job. It's awesome. Learning, learning a lot. Okay, so the last one I think is honestly more self-explanatory than this one. So the last one would be exponentiation. So given the same condition, if A is congruent to B mod M, then what do we get? A to the power of E will be congruent to B to the power of E mod M. Okay, I'll give you guys an example. We'll plug it in, and then it should be pretty simple. So let's just say 7 is congruent to 5 mod 2. Let's just take E to be 2. Can you guys just apply it and find what, in this case, 7 to the power of 2 is congruent to? Yeah, awesome. Someone's already got it. Nice, guys. If you're taking a bit of time, don't worry, I can go through it. But remember, it's like the same thing as like normal arithmetic in this case. If A equals to B, then A squared will be equal to B squared. Okay, so I'm not sure about how everyone is going right now, but I've gotten a couple of really good answers. So that would be 25, right? Because you just take 5 to the power of 2. So then 49 will be congruent to 25 mod 2. And what I've talked about before is that, mod 2 will tell you whether a number is even or odd. So if they're two odd numbers, then they'll definitely be congruent number in mod 2. So then obviously we're right here. Let's do maybe one more example just to check our understandings. So let's just say 5 is congruent to 3. Let's just do mod 2 again. If E equals to 3, what do we get? Awesome, Jackie. Really good. anyone else? I guess we're dealing with to the power of 3 here, so it might take a bit longer. Oh, awesome. How many more answers is that? That's like 4 more new answers all of a sudden. Good job, everyone. That's so good. So 5 is congruent to 3. I mean, sorry, 5 to the power of 3 is congruent to 3 to the power of 3 mod 2. Then 125 is congruent to 27 mod 2. Yeah, all good. I know what you meant. Awesome. So then we can move on from this. That's really, really good. Okay, I'll stop sharing. I will upload these notes later as well, though, so don't worry. Yeah, good job. Good job, Tara. Awesome. Okay. I'll share my laptop screen again so we can go back to the slides. Okay, so I just want to warn you guys, like the next part is gonna maybe look a bit harder because you'll have random names, maybe a bit of jargon, but I'll break it down, and I promise, like, we already have the power to learn these concepts because everything that we need, we've already actually learned. It's just about, understanding what these random symbols mean and things like that. So don't be, deterred. We will break it down. So some more number theory concepts. Divisors. Just quickly, can anyone tell me what a devise is? I know I was saying it's going to be, really complicated, but this is the first concept. So can just someone tell me what this is? Like, yeah, a number that you can divide, yeah, or divide into each other. Good job. A number that's divided by a factor, numbers that make up a number. Yeah, so, okay, we all get the gist of it. This is going to be something, as I've said before, it's something pretty important in modular arithmetic, so just making sure we can go with that. Now, we have the kind of, bigger part of the session, which would be Fermat's little theorem. So theorems can be tricky to prove or hard to understand, but they're really important and helpful to apply in Maths Olympiad and problem solving. So here's a note on using theorems though, like, because once you know these concepts, you'll be able to use them like almost immediately. But the thing is, it's really important to quote them and be like, by Fermat's little theorem, this property is true. Because otherwise the examiner might not know what you're talking about, and then they might deduct marks and things like that. So it's always important to clearly state Fermat's little theorem or things like that, or Fermat's theorem, just to make it clear. So what do we use this for? We use this for simplifying the computation of exponents. So given a certain, condition, once again, if a is an integer and p is a prime number, so we've gone over what prime numbers are, right? They're only divisible by themselves and 1. Then the following 3 conditions are true, and they're basically equivalent. The last one, we just need to know that it's only true if a is not divisible by p. But let's just break this down. So I think we've seen the notation all before, but I'll just probably say it verbally so we can kind of process it, because it's a lot to look at, right? So for the first one, we have a to the power of p is congruent to a mod p. So when a to the power of p is divided by a prime number p, then the remainder will be a. And in a similar way, we get to the second statement just by subtracting a from both sides. And we know that this works because of the addition subtraction principle that we talked about before. So a to the power of p minus a, so we're subtracting a from both sides to get to the second equation, so that we get 0 on the right hand side, mod p. So what that means is that a to the power of p minus a is an integer multiple of p. And then the last one is what we get by dividing both sides by a. Does that make any sense, guys? Because I know it's like a lot to look at sometimes, but the like concepts I feel like we've probably seen before. The best way to probably understand this is by doing a few problems. And I think I have got a few problems in the handout. So it would be good if you guys could, open up your handouts, but I will write the problems out on my iPad as well. So I'm going to share screen again. Actually, yes, I'll share screen again. Okay. Okay. So Fermat's little theorem. And Fermat is a person, by the way. He is a mathematician. So the statement that we're going to use for now will just be the first one, because this is just the one that I guess I kind of prefer it. Yeah, but different ones can be useful at different times as well. So, does everyone know what this means? Like when I explained it briefly before, like, does everyone understand the notation? What A and P are? Can I get like a show of hands, thumbs up, or like a private message saying no? Like, okay, yeah, I'll do a few examples. Yeah, this is the first one, and probably like the only one that you need right now for at least the session. Yeah, guys, don't worry if you're finding it a bit hard. This is like our last number theory session, so this is why it's like kind of ramping up a bit, but don't worry about it. It's like a pretty, they're all hard concepts to pick up. Yeah, but I'll try my best to explain this. So it's just another one of these rules, right? With a fancy name. Like it's the same as saying, A plus C is congruent to B plus D and whatever. It's like the same thing. It's just another rule that we want to use. So an example would just be to plug it in again. So let's just say A is 5, okay? Then P is a prime. Does someone want to pick a prime number for me? Anyone, just type in chat a prime number. Yeah, sure, 2. I got a 2 fast, but I'm getting, nice numbers, 2 and 3, not too hard to compute. I thought you guys would give me like 11 and stuff. And then, yeah, I did not want to, figure out 5 to the power of 11. But yeah, so let's do A equals 5, then P equals to 2. So then we get A to the power of P would be 5 to the power of 2, which would be congruent to A, which is 5 in mod 2. And then we can see that's true. 25 is indeed congruent to 5 in mod 2, because they're both odd numbers. So it's just a way of like figuring things out when they're like pretty, especially when the exponents are really big. Because, like, let's just like ignore this part. 25 and 5 are pretty small numbers. Why is it congruent again? Oh yeah, the proof is like a bit complicated, I think. So we're just not going to talk about that, because for theorems, like a lot of proofs are really, really difficult. So the most important thing is probably knowing how to apply them and just kind of memorizing them rather than knowing why exactly they work, because the explanation will be quite difficult. Like these types of theorems generally take so many years to prove, decades or hundreds of years. So the most important thing for us is just knowing how to use them. So for 25 and 5, it's a relatively easy example. But the really cool thing happens when we have even bigger powers. So if we had a equals 5, but p equals to like 23, then this property would still be true. 5 to the power of 23 would be congruent to 5 mod 23. And that's pretty cool because you're dealing with such big numbers. And then you're like, wow, you can simplify it from 5 to the power of 23, which is this absolutely huge number, down to just 5. Yeah, so that's the gist of it. Do we kind of understand it now? How? Oh, so I'm just telling, so this is like an identity. This is always true. So we can choose any integer, take it to the power of a prime number, and it will be congruent to that integer considering the modulus of that prime number. And this is true because Fermat proved it. And we're not going to prove it today, but know that it's true and use it. And that's the important part. So another example, like I get that some of you guys will be asking how, but I just want to make sure you guys know how to use it because we only have 9 minutes. Oh my gosh. Okay, yeah. So we'll just get through this. So I want to get to a problem so that we can see how this can be used. So find 3 to the power of 31 mod 7. This is the first question in our handout. Wow, good job. Yeah, I know, it's really cool, right? Because like it's such big numbers, but it's always going to be true. Good job, Jackie. So someone's already got it. Can anyone tell me? Or can anyone else tell me? Oh wait, this one's a bit harder actually, but it should be fine, I think. Wait, I need to check your answers. Hold on, let me just do it as well, just to make sure, because I did not check the answers before class, unfortunately. I thought mod and exponent had to be the same. Yeah, good question. That's a really good point. Yeah, exactly. So that's why this question is a little harder. Okay, I'm just gonna check the answer real quick, but think about how you can break it down. Because of the multiplication rule, we can split 3 to the power of 31 up into a few parts actually. So it would be good if we could think about using that rule as well. It's quite a bit to piece together, but I think a problem like this does really show you what we can actually do. Yeah, sorry, Jackie, I've read it wrong myself actually, but I'm doing the right. I'm figuring it out as well right now. Yeah. Oh wait, Jackie, I think you're right. No, I think you're right actually. Because I just did it and then I think I did get that. Okay, I'll just go on with this and then give you guys a hint to figure it out. So Tara made a really good point before about how like the exponent and the mod have to be the same. So then why don't we just like, consider the parts that are the same first? Because what mod 31, no, 3 to the power of 31 equals to is 3 to the power of 7. Sorry. To the power of 4 times 3 to the power of 3. Because that's 3 to the power of 28 times 3 to the power of 3, which equals to 3 to the power of 31, right? So if we use this part instead, we can break down things and make it a lot easier. Oh, we're trying to find what this is. Yeah. Okay. I'll just make it. I'm just gonna move some stuff around so we can have more space. Okay, but does this help at all? Because this means that we can use the property that we wanted before, right? We can instead use 3 to the power of 7 and find what that is in mod 7. Can anyone tell me what 3 to the power of 7 is congruent to in mod 7? Yeah, good job. Anyone else? Nice. So we want to use a rule from before. Yeah, good job, Regina. So again, we're plugging it in. Yeah, what is it congruent to? Or do you want me to say the answer? Oh yeah, okay. So then it's going to be congruent to 3, right? Because we have the prime p, which would be 7, the modulus p, which would be 7, then we have a and a. Awesome, awesome. Good job, guys. Okay, so hopefully that makes sense. So what we want to do is just plug it in. Then, what we're going to do now is we're going to use the exponent rule. So, if 3 to the power of 7 is congruent to 3, then what would 3 to the power of 28 be congruent to? 3 to the power of what? What goes in the box? Good job. Good job. One person's got it. Not quite. The number's smaller than that. Okay. Well, 3 to the power of 7 to the power of 4 equals to 3 to the power of 28. So we want to take both sides to the power of 4. That's the exponent rule, right? A to the power of e is congruent to b to the power of e mod m. Yeah. So we want to do 4 on both sides. Because what you're doing here is you're doing 3 to the power of 7 to the power of 4. Then you want to do 3 to the power of 4. So in this box, well, let's just remove the box, really. Then we get 3 to the power of 4 mod 7. And 3 to the power of 4 is not a big number. That's just going to be congruent to 81. And then we want to deal with smaller numbers again. So can anyone tell me what the remainder of 81 is when divided by 7? The remainder of 81 when divided by 7. Yep. Okay, good job. I'd assume everyone knows that. So that's going to be congruent to 4 mod 7. Okay, and then now we still want to account for this. 3 to the power of 3. I think it's a small number. It's just 27, right? I kind of have to speed through a little bit because we're running out of time. So I hope you guys don't mind too much. But then what we get would be 27 is congruent to 6 mod 7. Because of the multiplication rule, we can use this and use this. So then we want to find 3 to the power of 28 times 3 to the power of 3, which would be congruent to 4 times 6 mod 7, which equals to 24, which is congruent to 3 mod 7. So, sorry I had to rush through the end. It's quite a complex one because you have to kind of use all of the rules that we've done before. But at the end of the day, you think about it and you're like, you know, it's kind of hard, but we've actually done all of these rules before. Like we used this one theorem that we've just learned. We used the multiplication one, and we also used the exponentiation one. And that's a lot of rules, right? Oh, so what's the answer? I don't know if that was before or after I said it, but it was, the answer's 3. Yeah, that's the answer. So we use a bunch of rules, and that's the kind of process that you can expect to go through when you're doing a problem like these ones. So I have a couple more. I'll be uploading this recording later, so there are a few more in the handout. If anyone wants to do it as homework, optional homework, you can feel free to do it and send me your answers. And then I'll be happy to check them and things like that. Otherwise, since we don't have much time, well, we actually don't have any time, I'll just quickly share my screen again, and then I'll show you what else we would have like gone through, and then you guys can go through that in your own time if you'd like. But otherwise, this will be our last number theory session, and we'll be moving on to geometry next week, which I think is a lot of fun and it's not too complicated. So looks like someone already had to go. If you guys need to go, then you can go, but I'll just take 2 minutes to quickly, skip through the slides. The next thing that we would be, that you can choose to work on yourself would just be Euler's V function, which is just counting the number of primes up to a given integer that are relatively prime to it. More of that. And then the last thing is like kind of similar to the thing we did just before. It's like another theorem that we just know is always true. So these things have really cool applications. Actually, maybe before Tuesday, I can have another tutorial for like 20 minutes if anyone wants to talk about any of this. Yeah, before we move on to geometry. But otherwise, this is like the kind of content that is involved in number theory, maybe it's less on the fundamental side, which is what we were doing last session. It's more of on the elementary side, but these theorems can be super helpful. Yeah, and I think that if you're interested, feel free to learn them in your own time as well. Yeah, so as always, feel free to email me if you have any questions. You can email our like group account, our group's account, or you can email me personally as well if you have any like specific